Welcome to our next lecture in the series on condensed matter theory. In this lecture I want to talk about Wannier functions. And what we have seen before is that we can make Bloch states or Bloch wave functions from a set of local states or local wave functions or orbitals and use these as a convenient basis set to describe the eigenstates in our system. It is namely those Bloch states that are non-interacting or eigenstates of the crystal momentum, so they respect the symmetry of your system, and therefore you block diagonalize your Hamiltonian already with respect to crystal momentum. What I want to do today is focus a bit more on what these local states actually are. So we can make our Bloch wave function as a function of crystal momentum and some quantum number, your band index, or the local quantum numbers that these Bloch wave functions inherit, a normalization, and then a sum over all lattice vectors, e to the I, kr, and then some local wave function. And we have seen that we can take, for example, the atomic wave functions for our local wave function, as you then already start with a basis that diagonalizes your local problem, and you only have to take into account the interactions in a kind of tight binding format with the neighbors. Now, if I have my Bloch waves as a function of momentum, I have different taus that linear combine to generate the eigenstates that I have. What I now can do is say, well, if I want to make a low energy Hamiltonian that only focuses on the states within a certain energy window, I know that my eigenstates as a function of band index can be written as a superposition of my Bloch waves, where I have now my Bloch wave as a function of crystal momentum and Bloch wave index I. Can we choose our local wave functions such that you describe only a single band? Or in other words, what is the local wave function that describes this band exactly? So can we choose omega tau of r minus r such that the Bloch waves that we form in this form are equivalent to the eigenstates that we have. And it shouldn't be a function of, that's a function of r. Or equivalently, alpha I tau is delta I tau. Each eigenstate is made of its own local wave function. And the answer is yes, we can do that. What we have here is very similar to a Fourier transform. So we can use an inverse Fourier transform to get back to our local wave functions, which we will now call Vanier functions, from the band eigenstates. So I have my normalization, I sum over all crystal momentum vectors. I can add an additional phase. I can come back to that later. Then we have e to the minus I, k dot r, and then the band eigenstate k tau dot r. Band eigenstates are defined up to a phase, or a state is represented by a wave function times an arbitrary phase. I can use that to put in an extra degree of freedom here, and I can choose this phase function arbitrary as I like. I will always get a Wannier function that describes this band exactly. Of course, where the block state would not change, the local wave function will definitely depend on how I choose this phase function. But let me first prove that this is indeed a local Wannier function, such that when we generate block waves out of them, we get the eigenstates. So I can take this Wannier function, this local function, put it into our definition of a block wave and see what my block wave will be, which is the sum 1 over square root of v, the sum over all lattice sides, e to the I, k dot r, and now I have to put in my Wannier function, sum over k prime, e to the I theta k prime, e to the minus I k prime dot r, and then the band eigenstate at k prime with quantum number tau or band index tau. If we work this out, this is 1 over v times 1 over v square root is 1 over v. Then we have a sum over all lattice sides, all crystal momenta, e to the I k minus k prime dot r, our phase function k prime, and the eigenstate k prime tau. What we have here is a function that oscillates. You sum over all r, so only when k is equal to k prime this is going to contribute. At that point it is 1, it is sum over v over the entire volume, so 1 over v times this sum is exactly 1, so this is just the delta function between k and k prime. Which means we are left with e to the I theta k times the eigenstate that we have. So indeed, by choosing your Wannier functions as an inverse Fourier transform of the bands, you will find that taking those as local functions give you block waves, because it's just a Fourier in an inverse Fourier transform with an additional phase. But that's okay, because a wave function times a phase function is still an eigenstate when the first one was an eigenstate. So now the question is, how do we choose this phase function? And we can use this phase function to deliver some properties or determine some properties of our Wannier function. And let me discuss two common choices one can make. We want our Wannier function to be localized, and we can choose it to be maximal localized. A proof that you can always localize this actually is available in the literature. It is surprisingly long to prove that this Wannier function exponentially decays. We can have a reasonable understanding why this has to be the case. If I have a band that is smooth, then the tight binding parameters in one dimension are just given by the Fourier transform of the curvature of this band. So the nearest neighbor is the first order, the second nearest neighbor is the second order in the Fourier transform. When your bands are smooth, the higher frequencies should decay, so your hopping should be short-ranged. If your long-range hopping is 0, and your long-range hopping is given by a non-zero potential times the wave functions at a distance r, then that becomes 0 and your wave functions become 0. So you have to be short-ranged. Now, to write this down in a mathematical sound way that shows that you exponentially decay for a certain smoothness of your bands, with all possible exceptions, is extremely cumbersome or evolved. So I think the proof goes over 30 pages or so. So let's not do it here. But we can try to maximally localize our wave function. And for that we can say, well, I have my Wannier function. I can calculate the expectation value of r squared, and I want to minimize this. So this is 1 over v times the sum over 2k vectors e to the I, and then we have our phase function theta at k minus theta at k prime, and then we have the inner product of the band eigenstates k prime tau r squared, or the expectation value of r squared between the Wannier functions, the band states, sorry. And this is what we want to minimize. Now you already see that this is not a trivial minimization routine, and finding the maximum localized functions is numerically possible, but not an extremely trivial solution. When you think about it, it's nice to have a fully localized wave function, because that makes the shortest hopping range that you can think of, the most tight binding solution one can think of. But it's probably not the most physical sound starting point. In a solid, or in an atom, we have a detailed balance between kinetic and potential energy. In an atom, if we minimize the potential energy, the electrons would just go to delta functions that sit at the nucleus, which would give you an infinite potential energy. But at the same time, we know that the delta function, if you expand it on plane waves, you need all wave factors, and therefore the kinetic energy would also go to infinite. So that is not the lowest energy state. We can, of course, try to find a lowest energy state for the Wannier function close to the atom, close to the nucleus where they are bound, which means we would not want to minimize the localization or maximize the localization, minimize its radius, which is optimizing the potential energy, but we want to find a balance between kinetic and potential energy. And that is exactly what the atomic eigenstates do. They optimize or minimize the total energy, which is a balance between kinetic and potential energy. So instead of looking at maximum localized Wannier orbitals, we can look at maximal atomic-like. For that, we have to maximize the overlap between the Wannier function and an atomic orbital with quantum numbers L, m sigma and Lm sigma. So the principal quantum number, the angular momentum, the projection of the angular momentum on the z direction, and the spin. And this is just given by the square root 1 over v, sum over all crystal momenta, your phase function e to the I theta k, then the band eigenstate times the atomic orbital. Now, this sum is maximal when what we have in here is real and positive. If you're summing a set of complex numbers and you can change the phase of that complex number but not its norm, then you get the maximum out when the phase of all of those functions is the same and positive. So we want this phase to be cancelling the phase of our overlap. So for any k vector, we want theta k to be the argument of the overlap between the eigenstate and the atomic wave function, such that this is nicely a positive number for each k vector. So this is a much easier procedure to handle than finding maximum localized wave functions, and it's also nicely optimizing not just the potential energy, but optimizing the balance between potential and kinetic energy, which is the much more physical solution that you want to look at. So when we've been talking about tight binding models and say, well, we can start from atomic wave functions, I actually had in mind that we were starting with Wannier functions that are maximal atomic-like, and of course, when you do one band, that is the procedure that I've discussed here. When you do more than one band, you still have the freedom to linear combine the wave functions of different orbitals, the bands of different the wave functions of different bands, so that you don't have to look at a mixture of S and P, for example, for both bands, but you can make one S-like Wannier function and one P-like Wannier function. And it turns out that for real materials, these maximal atomic-like Wannier functions are actually pretty atomic-like. We will show a few examples later, and then you will see that you just really recognize the atomic wave functions in them. And you have overlaps of more than 90% in several cases. So yes, you have still a lot of atomic character, even for materials like the alkali metals that are basically free electron-like. Now, the reason that I prefer the Wannier functions over a set of atomic orbitals has to do with the fact that the Wannier functions form an orthonormal basis set, whereas the atomic orbitals are not. So let me prove that the Wannier functions are orthonormal. And we have our Wannier function sitting at side R with quantum number tau, a Wannier function sitting at side R prime with quantum number tau prime. And the statement is that these are delta functions between R and R prime and tau prime. So this is 1 over V, the sum over the crystal momentum of one and the other. I'm going to do the Fourier transform to go to my band eigenstates, and one for the left and one for the right. One for the bra, one for the ket, e to the k prime dot r prime minus k dot r. And then we have the inner product of the band eigenstates, k tau, k prime, tau prime. And this is just a delta function between the two crystal momenta and a delta function between the band indices. So what we have is 1 over V, sum over a single crystal momentum, e to the I, crystal momentum dot r prime minus r, delta tau, tau prime. The delta k prime is eaten by one of the sums, and I can just make them equal. There's no k on the left. And this is again a sum over all k vectors of the difference. This is an oscillating function except when r prime is equal to r. So this is delta r prime, delta tau, tau prime. This is exactly what we wanted to show, that our Wannier functions form an orthonormal basis set. So very often we will talk about bands and band structure, and we will talk about an S band and a P band, thinking of the atomic character that we have, and then we refer to orthonormal basis sets. So we talk about the maximal atomic-like Wannier functions that we have and the character that we have in there. And because these are very close to the atomic wave functions, there's no need to actually make that distinguish when you want to talk about the physical interpretation and the symmetries that follow from this. But you do need to realize that, well, if you make a band structure of hydrogen atoms and you start from the 1s, then there will be some admixture of the 2s and the 3s in there to form the eigenstates. But in general, at normal pressures, that mixture will be small. Well, it costs energy to make excitations from 1s into 2s, a Rydberg order of energy, which is a lot. So you want not to admix too much of those higher lying states. So that's why we talk a lot about the atomic character in our states. Carbon makes wave functions, or the bands in graphene form from the 2s and the 2p orbitals in that material. And we'll show later by examples that indeed that works pretty well. Thank you very much. We'll see each other later. Stay healthy.